Hi, thank you for joining me. We're talking about resonance in Lewis dot structures, and to resonate means to match energy. So resonance occurs when there's more than one, and this is key, equivalent Lewis dot structures. In another video, I'll address a situation where they are not of equal energy. Now note, the molecules do not transition from one structure to the next. The actual structure is defined as kind of a blend or a hybrid or maybe an average of the resonance structures. And those electrons have a lot of freedom of motion. So we say they are delocalized. So if I draw the Lewis dot structure for oxygen, okay, so I've got 6 plus 6 plus 6 or 18 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, the one on the left, and randomly, the one, it could have been the right. I just picked one to start with. That one ends up with the double bond. But that double bond could have very readily been put on this other oxygen. So we have resonance in this case. We have a sulfur to an oxygen. There has to be a full bond. Don't forget that non-bonded pair. But what is different is I have a partial bond that we will designate with dots because it's not a full bond. This would be an AB2E structure. Okay? And these are delocalized. Our bond order, some of you can see it intuitively, but we can calculate it. We have the number of bonds, not electrons, but electron pairs is 2, 1, 2, 3. So I have 3 bonds to that sulfur, and they're shared by 2 peripheral atoms. So my bond order is 1 and 1/2. Again, you'll typically see bond orders of 1, 1 1/3, 1 1/2, 2, and 3. Now, benzene has 6 carbons and a ring and 6 hydrogens. So we have C, 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 and as you see, okay, so I've got bonds to hydrogen. Remember, hydrogen can only have 1 bond. So each carbon's going to have 1 bond. Now, each hydrogen, will have 1 bond to carbon. Now, carbons must have 4 bonds. That's a good trick for doing things a little more quickly, is just counting to make sure carbon has 4 bonds to it. So now that I added this double bond, this one has 1, 2, 3, 4. This one has 1, 2, 3, 4. This one only has 1, 2, 3. I can't put it here, or it would give that carbon 5, and it can't have 5. So I'm going to put it here, and I'm going to put one here. Okay? But as you see, there's no reason, somebody else could have been drawing the same structure, and those are hydrogens coming off. Okay, another person very reasonably could have drawn this structure with the double bonds in these opposite locations. So there is resonance, equal energy possibilities for those double bonds. In reality is a blend of these, and the bond order would be 1 and 1/2 for each of those. And let me show you what that would look like. We'd have a carbon. So you'll often see a benzene ring, and I'm writing all these hydrogens, but organic chemists skip them. You'll see it with this dotted circle because those electrons are delocalized and allowed to move. So that would be benzene. In fact, a simple drawing of benzene just shows carbons at the corners with a circle in the middle. So organic chemists really like to streamline their work. So let's take a look at the impact of bond order on bond length and bond energy. So as your bond order increases, your bond length decreases. I encourage you to read this. I did it intentionally trying to make a little fun, but it's got important information in there. Your bond length decreases because there's more electron density between the atoms. The bond energy increases. Again, the more electron density it is, that you've got stronger, tighter attractions, and it's going to take more energy to break. Remember, it takes to break. So, hopefully this has been a good boost for you to help you with your chemistry. Thanks for joining me.